Unbiquadium. Unbiquadium, also known as element 124 or eka-uranium, is the hypothetical chemical element with atomic number 124 and placeholder symbol UP. Unbiquadium and UP are the temporary IUPAC name and symbol, respectively, until the element is discovered, confirmed, and a permanent name is decided upon. In the periodic table, Unbiquadium is expected to be a G-block superactinide and the sixth element in the eighth period. Unbiquadium has attracted attention, as it may lie within the island of stability, leading to longer half-lives, especially for 308 UP, which is predicted to have a magic number of neutrons 184. Despite several searches, Unbiquadium has not been synthesized, nor have any naturally occurring isotopes been found to exist. It is believed that the synthesis of Unbiquadium will be far more challenging than that of lighter undiscovered elements, and nuclear instability may pose further difficulties in identifying Unbiquadium unless the island of stability has a stronger stabilizing effect than predicted in this region. As a member of the superactinide series, Unbiquadium is expected to bear some resemblance to its possible lighter congener uranium. The valence electrons of Unbiquadium are expected to participate in chemical reactions fairly easily, though relativistic effects may significantly influence some of its properties. For example, the electron configuration has been calculated to differ considerably from the one predicted by the Aufbau principle. Introduction. The heaviest atomic nuclei are created in nuclear reactions that combine two other nuclei of unequal size into one, roughly. The more unequal the two nuclei in terms of mass, the greater the possibility that the two react. The material made of the heavier nuclei is made into a target, which is then bombarded by the beam of lighter nuclei. Two nuclei can only fuse into one if they approach each other closely enough. Normally, nuclei all positively charged repel each other due to electrostatic repulsion. A strong interaction can overcome this repulsion, but only within a very short distance from a nucleus. Beam nuclei are thus greatly accelerated in order to make such repulsion insignificant compared to the velocity of the beam nucleus. Coming close alone is not enough for two nuclei to fuse. When two nuclei approach each other, they usually remain together for approximately 10-20 seconds and then part ways, not necessarily in the same composition as before the reaction, rather than form a single nucleus. If fusion does occur, the temporary merger termed a compound nucleus is an excited state. To lose its excitation energy and reach a more stable state, a compound nucleus either fissions or ejects one or several neutrons, which carry away the energy. This occurs in approximately 10-16 seconds after the initial collision. The beam passes through the target and reaches the next chamber. The separator, if a new nucleus is produced, it is carried with this beam. In the separator, the newly produced nucleus is separated from other nuclides, that of the original beam and any other reaction products, and transferred to a surface barrier detector, which stops the nucleus. The exact location of the upcoming impact on the detector is marked. Also marked are its energy and the time of the arrival. The transfer takes about 10-6 seconds in order to be detected. The nucleus must survive this long. The nucleus is recorded again once its decay is registered, and the location, the energy, and the time of the decay are measured. Stability of a nucleus is provided by the strong interaction. However, its range is very short. As nuclei become larger, their influence on the outermost nucleon's protons and neutrons weakens. At the same time, the nucleus is torn apart by electrostatic repulsion between protons, as it has unlimited range. Nuclei of the heaviest elements are thus theoretically predicted. Alpha decays are registered by the emitted alpha particles, and the decay products are easy to determine before the actual decay. If such a decay or a series of consecutive decays produces a known nucleus, the original product of a reaction can be determined arithmetically. Spontaneous fission, however, produces various nuclei as products, so the original nuclide cannot be determined from its daughters. The information available to physicists aiming to synthesize one of the heaviest elements is thus the information collected at the detector's location, energy, and time of arrival of a particle to the detector, and those of its decay. The physicists analyze this data and seek to conclude that it was indeed caused by a new element and could not have been caused by a different nuclide than the one claimed. Often, provided data is insufficient for a conclusion that a new element was definitely created and there is no other explanation for the observed effects, errors in interpreting data have been made. History. Synthesis attempts. Because complete nuclear shells or, equivalently, a magic number of protons or neutrons may confer additional stability on the nuclei of superheavy elements, moving closer to the center of the island of stability, it was thought that the synthesis of element 124 or nearby elements would populate longer-lived nuclei within the island. Scientists at Ganel Grand Accelerator National Downs attempted to measure the direct and delayed fission of compound nuclei of elements with C equals 114, 120, and 124 in order to probe shell effects in this region and to pinpoint the next spherical proton shell. In 2006, with full results published in 2008, the team provided results from a reaction involving the bombardment of a natural germanium target with uranium ions 23,892 U plus net 32 G 308 trillion, 310 billion, 311 million, 312,314 up asterisk fission. The team reported that they had been able to identify compound nuclei fissioning with half-lives 1018s. This result suggests a strong stabilizing effect at Z equals 124 and points to the next proton shell at Z 120, not at Z equals 114 as previously thought. A compound nucleus is a loose combination of nucleons that have not arranged themselves into nuclear shells yet. It has no internal structure and is held together only by the collision forces between the target and projectile nuclei. It is estimated that it requires around 1014s for the nucleons to arrange themselves into nuclear shells, at which point the compound nucleus becomes a nuclide, and this number is used by IUPAC as the minimum half-life. A claimed isotope must have to potentially be recognized as being discovered. Thus, the Ganel experiments do not count as a discovery of element 124. The fission of the compound nucleus 312,124 was also studied in 2006 at the Tandem ALPI Heavy Ion Accelerator at the Laboratory Nazionale, 23,290 Th plus 8,034 C312 up asterisk fission. Similarly to previous experiments conducted at the Jenner Joint Institute for Nuclear Research, fission fragments clustered around doubly magic nuclei such as 132 SNC equals 50 and equals 82, revealing a tendency. The average number of neutrons per fission from the 312,124 compound nucleus relative to lighter systems was also found to increase, confirming that the trend of heavier nuclei emitting more neutrons during fission continues into the superheavy mass region. Possible natural occurrence. A study in 1976 by a group of American researchers from several universities proposed that primordial superheavy elements, mainly livermorium, unbiquadium, unbihexium, and unbiseptium, could be a cause of unexplained radiation damage, particularly radiohalos, in minerals. Unbiquadium was then suggested to exist in nature with its possible congener uranium in detectable quantities at a relative abundance of 1011. Such unbiquadium nuclei were thought to undergo alpha decay with very long half-lives down to flerovium, which would then exist in natural lead at a similar concentration 1011 and undergo spontaneous fission. This prompted many researchers to search for them in nature from 1976 to 1983. A group led by Tom Cahill, a professor at the University of California at Davis, claimed in 1976 that they had detected alpha particles and X-rays with the right energies to cause the damage observed, supporting the presence of these elements. Others claimed that none had been detected and questioned the proposed characteristics of primordial superheavy nuclei. In particular, they cited that the magic number n equals 228 necessary for enhanced stability would create a neutron excessive nucleus in unbiquadium that would not be beta stable. This activity was also proposed to be caused by nuclear transmutations in natural cerium, raising further ambiguity upon this claimed observation of superheavy elements. The possible extent of primordial superheavy elements on Earth today is uncertain. Even if they are confirmed to have caused the radiation damage long ago, they might now have decayed to mere traces, or even be completely gone. It is also uncertain if such superheavy nuclei may be produced naturally at all, as spontaneous fission is expected to terminate the process responsible for heavy element formation between mass number 270 and 290, well before elements such as unbiquadium may be formed. Naming. Using the 1979 IUPAC recommendations, the element should be temporarily called unbiquadium symbol up until it is discovered, the discovery is confirmed, and a permanent name chosen. Although widely used in the chemical community on all levels, from chemistry classrooms to advanced textbooks, the recommendations are mostly ignored among scientists who work theoretically or experimentally on superheavy elements, who call it element 124 with the symbol ion 124, 124, or 124. Some researchers have also referred to unbiquadium as eka-uranium, a name derived from the system Dmitry Mendeleev used to predict unknown elements, though such an extrapolation might not work for G-block elements with no known congeners, and eka-uranium would instead refer to element 144 or 146 when the term is meant. Prospects for future synthesis. Every element from Mendelevium onward was produced in fusion evaporation reactions, culminating in the discovery of the heaviest known element oganesson in 2002 and more recently tennessine in 2010. These reactions approached the limit of current technology. For example, the synthesis of tennessine required 22 milligrams of 249 Bk and an intense 48 Ca beam for 6 months. The intensity of beams in superheavy element research cannot exceed 10-12 projectiles per second without damaging the target and detector and producing larger quantities of increasingly rare and unstable actinide targets is impractical. Consequently, future experiments must be done at facilities such as the under construction Superheavy Element Factory, factory at the Joint Institute for Nuclear Research JINR or RIKEN, which will allow experiments to run for longer stretches of time with increased detection capabilities and enable otherwise inaccessible reactions. Even so, it is expected to be a great challenge to continue past elements 120 or 121 given short predicted half-lives and low predicted cross-sections. The production of new superheavy elements will require projectiles heavier than 48 Ca, which was successfully used in the discovery of elements 114-118, though this necessitates more symmetric reactions which are less favorable. Hence, it is likely that the reactions between 58 Phi and a 249 CF or newly available 251 CF target are most promising. Studies on the fission of various superheavy compound nuclei have found that the dynamics of 48 Ca and 58 Phi-induced reactions are similar, suggesting that 58 Phi projectiles may be viable in producing superheavy nuclei up to Z equals 124 or possibly 125. It is also possible that a reaction with 251 CF will produce the compound nucleus 309 Ubq** with 185 neutrons immediately above the N equals 184 shell closure. For this reason, the compound nucleus is predicted to have relatively high survival probability and low neutron separation energy. These dynamics are highly speculative, as the cross-section may be far lower should trends in the production of elements 112-118 continue, or the fission barriers be lower than expected, regardless of shell effects, leading to decreased stability against spontaneous fission, which is of growing importance. Nonetheless, the prospect of reaching the N equals 184 predicted properties, nuclear stability in isotopes. Unbiquadium is of interest to researchers because of its possible location near the center of an island of stability, a theoretical region comprising longer-lived superheavy nuclei. Such an island of stability was first proposed by University of California professor Glenn Seaborg, specifically predicting a region of stability centered at element 126 unbiquadium and encompassing nearby elements, including unbiquadium, with half-lives possibly as long as 109 years. In known elements, the stability of nuclei decreases greatly with the increase in atomic number after uranium, the heaviest primordial element, so that all observed isotopes with an atomic number above 101 decay radioactively, with a half-life under a day, with an exception of Dubni-268 with half-life of 28 hours 1 day. Nevertheless, there is a slight increase in nuclear stability in nuclides around atomic numbers 110-114, which suggests the presence of an island of stability. This is attributed to the possible closure of nuclear shells in the superheavy mass region, with stabilizing effects that may lead to half-lives on the order of years or longer for some as yet undiscovered isotopes of these elements. While still unproven, the existence of superheavy elements as heavy as oganesson provides evidence of such stabilizing effects, as elements with an atomic number greater than approximately 104 are extremely unstable in models neglecting magic numbers. In this region of the periodic table, N equals 184 and N equals 228 have been proposed as closed neutron shells, and various atomic numbers have been proposed as closed proton shells, including Z equals 124. The island of stability is characterized by longer half-lives of nuclei located near these magic numbers, though the extent of stabilizing effects is uncertain due to predictions of weakening of the proton shell closures and possible loss of double magicity. More recent research predicts the island of stability to instead be centered at beta-stable copernicium isotopes 291 Cn and 293 Cn, which would place unbiquadium well above the island and result in short half-lives regardless of shell effects. A 2016 study on the decay properties of unbiquadium isotopes 284-339 Up predicts that 284-304 Up lie outside the proton drip line and thus 305-323 Up may undergo alpha decay, with some chains terminating as far as flerovium and heavier. These results, as well as those from a quantum tunneling model, predict no half-lives over a millisecond for isotopes lighter than 319 Up, as well as especially short half-lives for 309-314 Up in the submicrosecond range due to destabilizing effects immediately above the shell at N equals 184. This renders the identification of many unbiquadium isotopes nearly impossible with current technology, as detectors cannot distinguish rapid successive signals from alpha decays in a time period shorter than microseconds. Increasingly short spontaneous fission half-lives of superheavy nuclei and the possible domination of fission over alpha decay will also probably determine the stability of unbiquadium isotopes. While some fission half-lives constituting a sea of instability may be on the order of 1018s as a consequence of very low fission barriers, especially in even nuclei due to pairing effects, stabilizing effects at N equals 184 and N equals 228 may allow the existence of relatively long-lived isotopes. For N equals 184, fission half-lives may increase, though alpha half-lives are still expected to be on the order of microseconds or less, despite the shell closure at 308 Up. It is also possible that the island of stability may shift to the N equals 198 region, where total half-lives may be on the order of seconds, in contrast to neighboring isotopes that would undergo fission in less than a microsecond. In the neutron-rich region around n equals 228, alpha half-lives are also predicted to increase with increasing neutron number, meaning that the stability of such nuclei would primarily depend on the location of the beta stability line and resistance to fission. An early calculation by P. Mahler, a physicist at Los Alamos National Laboratory, estimates the total half-life of 352 up with n equals 228 to be around 67 seconds, and possibly the longest in the n equals 228 region. Chemical. Chemical. Unbiquadium, it's the fourth member of the superactinide series, and should be similar to uranium. Both elements have 6 valence electrons over a noble gas core. In the superactinide series, the off-bow principle is expected to break down due to relativistic effects, and an overlap of the 5th, 6th, 7th, and 8th orbitals is expected. The ground state electron configuration of unbiquadium is thus predicted to be Ag 638 pone or 628 in contrast to Ag 548 derived from off-bow. This predicted overlap of orbitals and uncertainty in order of filling, especially for f and g orbitals, renders predictions of chemical and atomic properties of these elements very difficult. One predicted oxidation state of unbiquadium is +6, which would exist in the halides up X6X equals a halogen, analogous to the known +6 oxidation state in uranium. Like the other early superactinides, the binding energies of unbiquadium's valence electrons are predicted to be small enough that all 6 should easily participate in chemical reactions. The predicted electron configuration of the up 5 ion is Ag 6 phone.